Hello, this is the ninth video of my multivariable calculus course. Last time we talked about tangent and normal vectors to curves. So the way we find the tangent vector to a curve is we parameterize the curve, we take the derivative of the position, and then we're going to take the magnitude of the derivative, and then we divide that derivative by its magnitude to get a unit vector. So why do we need a unit vector? Because we want it to not depend on our parameterization. We want to eliminate every other extraneous condition. So if we look at r prime, that is exactly the velocity, and then we're dividing the velocity by speed to get a unit vector. And then we also talked about how a normal vector would be r t prime derivative of the unit tangent vector divided by magnitude. So what is a normal vector? It's a vector that is perpendicular to the tangent vector. And then if we cross multiply the first one, we get v of t equals magnitude of v times t, and t prime is equal to magnitude of t prime times n. Now there's a relation, very interesting relation between this tangent vector and normal vector and acceleration. So how do we get that relation? We are going to take the derivative of velocity to get the acceleration. So that gives us a of t, that's the derivative of v. So this is exactly just v prime. Using product rule, we get derivative of magnitude of v times t of t plus magnitude of v times t prime of t. Evaluating t prime of t from the second equality, this equality, we get t prime is magnitude of t prime times n of t. And if we substitute, we get this equality that we have here. So this is the equality that we obtain. Now, what does that tell us? It tells us that if we look at a curve and look at the unit tangent vector, and then look at the unit normal vector, which is perpendicular to the other one, we can multiply t of t by a scalar and multiply n of t by another scalar, and notice that this a sub n is in fact not negative. And if we multiply these two by scalars and add them up, we get the acceleration. So what does it mean geometrically? It means acceleration, tangent vector, and n lie on the same plane. So these lie on the same plane. So if we want to find acceleration, we could just take a multiple of t plus a multiple of n, and that would give us the acceleration. And in fact, the coefficient of n in this one is in fact non-negative because it's product of two magnitudes. Okay, so there's also another way of evaluating these tangential and normal components of acceleration. So these two numbers, a sub t and a sub n, are called tangential and normal components of acceleration. Now there's another way of evaluating these two quantities. So let's talk about that. So if you look at the normal vector and the tangent vector, I'm going to evaluate a sub t and a sub n in terms of dot product and cross product. So if I drop a perpendicular here, and this is the velocity, this is going to be a sub t. If I call this angle theta, a sub t becomes magnitude of a times cosine of theta. And of course, that can be evaluated by dot product. So this is a dot v divided by magnitude of v. So that's another formula for a sub t. If we drop the perpendicular here, this would be a sub n. Another way of doing that would be to use this triangle. So a sub n is going to be magnitude of a times sine of theta, which we can evaluate by cross product. So a cross v divided by magnitude of v. Now, if you look at this right triangle right here, we could use the Pythagorean theorem. We get at squared plus an squared equals magnitude of a squared. Now, we know that a sub n cannot be negative. So we could solve this for a sub n without having to worry about plus minus. So we get square root of magnitude of a squared minus a sub t squared. So bottom line are these three formulas. So a sub t is v dot a divided by magnitude of a. A sub n is magnitude of a squared minus at squared. And the other formula for that would be the cross product of a and v divided by magnitude of v. So the first formula is easier to use when you want to find a sub n. Okay, so let's look at one example. They gave us a curve and they're asking us to find tangential and normal components of acceleration. So to evaluate those, we'll have to first find velocity. So velocity is going to be derivative of position. So we're simply going to take the derivative. We're going to get 1, 2, 2t. Next, we're going to find acceleration, which would mean we have to take the derivative of velocity. So this would be 0, 0, 2. Next, we're going to find the dot product of these two. A sub t is v dot a divided by magnitude of v. V dot a is 1 times 0 plus 2 times 0 plus 2t times 2 divided by magnitude of v, which is the square root of 1 plus 4 plus 4t squared. So this would be 4t over root 5 plus 4t squared. So this is a sub t. A sub n is evaluated by square root of magnitude of a squared minus a sub t squared, which is the square root of magnitude of a squared is magnitude of this squared, which is 4, minus a sub t squared, which is 16t squared over 5 plus 4t squared. And we can simplify this. So denominator is going to be 5 plus 4t squared, and numerator would be 20 plus 16t squared minus 16t squared, and we're going to have to take the square root of that. So a sub n is going to be root 20 over root 5 plus 4t squared, and a sub t was what we found earlier. So a sub t is going to be 4t divided by root 5 plus 4t squared. Okay, so let's move on to a different topic. So we're going to see some of the applications of this in the next section. So curvature. So what is the curvature of a curve in space? We think about curvature as something that shows how much a curve bends. So for example, if you have a line, we think about the curvature of this line as 0. We don't want to assign any curvature to this line. So we would like the curvature of this to be 0. If we have a circle that is a small as opposed to a circle that is large, at any point here, we are going to bend much faster than a point right here. Depending on the relation between the radii, the curvature can be determined. So if you have a radius 1, let's say here, and a radius, let's say 3, you expect the curvature of this one to be larger than the curvature of the one on the right. And the reason is when you walk along this one, you're going to bend much faster than when you walk along this one. You're going to bend slower. So how do we define this one? So it looks like it should be a rate of change. So what is the definition of curvature, which I usually denote that by kappa? So kappa at t is the derivative of the tangent vector relative to arc length function. So s of t is the arc length function. So we are going to take the rate of change of the tangent vector. So how fast does that change? So the faster it changes, the curvature would be larger, which matches our intuition. Now, from one of the things that we have seen before, if we look at the arc length function, that's evaluated by taking the magnitude of r prime of u du from t0 to t, which means ds dt by the fundamental theorem of calculus is magnitude of r prime of t, or another way would be to say v. So let's now use this to evaluate kappa. So if you look at dt dt, this is going to be by the chain rule, this is dt ds times ds dt. Let's take the magnitude. The left side is just the magnitude of t prime equals this guy. When you take the magnitude of this, it's exactly kappa of t. And this guy is exactly what we found up here, which is magnitude of v. So that tells us kappa is equal to magnitude of t prime divided by magnitude of velocity, which is the speed. Now, let's look at one of the things that we had seen before. So we saw that a sub n was, if we go back and look at the formulas that we got, we saw that a sub n is magnitude of v cross a divided by magnitude of v. So this is magnitude of v cross a divided by magnitude of v. But we had another formula for a sub n as well. If we go back and look at the other formula that we got earlier, at the kind of early on, we got that a sub n is magnitude of v times magnitude of, so this is what I'm using here, a sub n is magnitude of v times magnitude of t prime. So let's use that. We get magnitude of v times magnitude of t prime. Let us solve for t prime so that we can plug it right here. So that gives us magnitude of t prime is equal to magnitude of v cross a divided by magnitude of v squared. And if we take that and plug it into the bottom, into the top, we get curvature is equal to magnitude of v cross a divided by, so we'll have to divide this by magnitude of v. So divided by magnitude of v cubed. So this is the curvature at any point. So let's do an example, and that's the formula that I have summarized here. So let's do two examples on this. Find the curvature of a circle of radius r. So in order to find the curvature, we need to find velocity and acceleration, find the cross product, and then divide the magnitude of, by the magnitude of velocity cubed. So the first thing is we need to find the velocity. But in order to find the velocity, we need a parametrization. So let's just start with the parametrization. Parametrization for a circle of radius r would be r cosine t, r sine of t. Now, because eventually we would like to take cross product, we will have to put these vectors in three-dimensional space, which means we'll have to put a 0 at the end. So given that, we can find velocity. So velocity, I'm not going to put the t's in there. It's minus sine t, r cosine t, 0. Acceleration would be minus r cosine t, minus r sine t, 0. Let's take the cross product of these two, v cross a. That is going to be I, j, k minus r sine t, r cosine t, 0 minus r cosine t minus r sine t, and 0. So let's expand along the first row. We get I times 0 minus 0 minus j times, so again we get 0 minus 0 plus k times r squared sine squared of t plus r squared cosine squared of t, which is r squared k. So next we're going to have to take the magnitude of this. So magnitude of v cross a is going to be square root of r to the fourth, which is r squared. Now we'll have to divide that by magnitude of v cubed. So magnitude of v is going to be square root of, so v is given as minus r sine, r cosine. So squaring those, we get r squared sine squared plus r squared cosine squared, and then 0 squared. So that would be root r squared, which is r. So curvature is going to be magnitude of v cross a, which is r squared, divided by magnitude of v cubed. So that's 1 over r. So this would be the curvature of a circle. Does it match with our intuition? Yes. So the larger the radius, the smaller the curvature, because it bends slower. Find the curvature of the graph y equals x squared in the xy plane at point 1, comma 1. Okay, so again, we need to first start with the parameterization. So r of t equals, since it is a graph of a function, the way we parameterize graphs of functions is by t comma f of t. So this would be t comma t squared. But since again we are trying to find a cross product at the end, I'm going to put a 0 at the end. Then we're going to evaluate the velocity, which would be just differentiating this. That would give us 1, 2t, 0. Next, we're going to find the acceleration. So this would be 0, 2, 0. Then we're going to plug in the values to get to this point. So 1, comma 1 gives t equals 1. Because this one and this one would have to be 1. So that means t equals 1. So that means velocity would be 1, 2, 0. And acceleration would be 0, 2, 0. So now we have to find the cross product of a and v. This would be I, j, k, 1, 2, 0, 0, 2, 0. So let's evaluate this. So this is I times 0 minus 0. The determinant of this is 0 minus 0. And then j times, that's also 0 minus 0. And then plus k times 2 minus 0. So that is 2k. So that's v cross a. We will find the cross product of these two, and then we find the magnitude. So that would be 2. And then we find the magnitude of v. Magnitude of v is square root of 5, square root of 1 squared plus 2 squared plus z squared, 0 squared. So kappa at t equals 1 would be magnitude of a cross v divided by root 5 cubed. So the answer is 2 over 5 root 5. So this is the curvature of the graph of the function y equals x squared at point 1, comma 1. To summarize, we talked about tangential and normal components of acceleration. We talked about how to find them, and then we talked about how to find curvature. So I will see you in the next video.